Now, let's further move to the third kind of moment, which is called the moment due to a couple. This is also the special case of the previous one, but this time, the ideal scenario is this time we are dealing with two forces. So what are the moment of these two forces about a given point? Before we talk about what are the moment of two forces about a given point, first of all, we need to carefully define these two forces, because these are the two special forces, not two arbitrary forces you can get and then you calculate the moment. That's not the deal we're talking about with the so-called moment due to a couple. The couple means there are two forces. Number one, both forces have the same magnitude, number one. Number two, they are parallel. And number three, they are in different directions, in opposite directions. Satisfying three requirements form a couple. And then the next question is, what is the moment due to this couple? Or what's the moment due to these two forces? And that is the third kind of moment we're going to introduce. Moment due to a couple. Okay? So first of all, let's see we have a couple, or we have two special forces. So we have one force going to that direction, the other force going to the opposite direction. Number one, these two forces must have the same magnitude. If this is a 100 pounds vector, this must be a 100 pounds vector as well. Not only that, these two forces are parallel. And number three, they are in opposite direction. So then the question is, what is the moment of due to these two forces? This time, when we say moment due to a couple, we didn't say at a certain point. And the reason we didn't say at a certain point is because the result is independent from any point you pick. Okay? If you don't believe it, let's give it a try. Now we have two special forces forming a couple because this force and this force have the same magnitude. They are parallel. Number three, this is in the opposite direction of F. Then, to calculate the moment of this force and calculate the moment of this force, I just randomly pick a point. Okay? So I pick point O. I randomly pick this point O, and then I establish the coordinate system at point O. But this point O is I randomly picked. I didn't say this point O to this one has to be 10 or has to be 20 at any distance. So what is the moment of this force at this point? What is the moment of this force at this point? And we put them together because first kind of moment is always a vector. We can add them together, right? Okay. The moment of this force about point O is this. The moment of this force at point O is the distance vector we call r from the point you want to calculate the moment of to the point the force applied on, that's point A, that's from O to A. So from O to A, that's a vector RA cross F. So that's why I'm writing R cross A, R distance vector cross force vector. So this is the moment of this force about this arbitrary point we picked. Then we have another force acting on point B. What is the moment of the other force at point B? What is the other moment of this force at the same point O we randomly pick? So then it's going to be the distance vector from O to this point that other force applied. It's called OB, right? So from O to B. So that is another distance vector RB from O to B. And then cross this force. But this force is the negative of this one, so that's why I put negative F. This is F, but this is in the opposite direction. That's why I have negative F. So, and then we add them together because this is the moment due to the first force, this is the moment due to the second force, but I want to see the combined result, the effect. So then I just add them together. When I add them together, you have a common term called F. I'm going to put the F outside. So then you're going to have RA minus RB. This is RA, and this is RB. Okay, so this is RA, this is RB. A is any point in this force line. B is any point in this force line. And they are, of course, parallel. So RA subtract RB from basic vector operation, that is the vector from B to A. It's a vector from B to A. And I call this is R. See, after we do this operation, we finally end up with the total moment due to these two special forces. In other words, the total moment due to this special couple, that's equal to R cross F. And this is a very significant result. It's because, number one, from this result, we find out the final moment is independent from this point O, right? Because somewhere in between, that's related with point O, because this is from O to A, this is from O to B. But after you combine them together, you finally end up with something independent from the point O you chose. It's only related with the distance vector R, which is the distance vector from any point for the second force to any point of the first force. And that's called R. Of course, you say, well, that's from B to A. But the B is arbitrary and A is arbitrary. B is at any point along this. A is any point along this. So that's the distance vector from any point of the second force line to any point on the first force line. And then cross the first force vector. So this is not negative F. This is F. In other words, this is the first force. Okay? So this is the result of the third kind of moment, which is the moment due to a couple. So how to calculate moment due to a couple due to those two special forces? You just need to find R vector and then cross the first force vector. If you say this is my first force and this is my second force, then how I'm going to choose R? If that's the case, you randomly pick up any point from the second force to any point to the first force. So this is R, and then cross negative F. But this R is always a negative of this R. So then negative times negative equal to positive as well. So it doesn't matter which one you call the first force, which one you call the second force. The end result is still the same. Okay? The bottom line is, if you assume this is the first force, this is the second force, then the distance vector is from any point of the second force direction to any point in the first force direction. That's called R. And then cross the first force. Okay? Further, because sometimes we deal with a two-dimensional problem, we still try to find what we call the short distance. So if that's the case, what is R cross F? By definition, the magnitude of this R, that means this is distance, not vector, multiplied with the magnitude of this F, and then times the sine of the angle between these two vectors. So you have vector R, you have force F, and obviously this is the angle between these two vectors. So then what's the sine of this one? So R multiplies sine theta. This is R times sine theta, that's D. So this D is what? It's also called a short distance, but this time it's a short distance between two parallel lines. So if we have two parallel lines, then the short distance is fixed. So you don't need to worry about from which point you want to shoot. You can choose any point, and then you can find out the short distance between these two vectors. Okay? Because they are all parallel. So this is an equation sometimes we use to calculate the magnitude of this third type of moment, which is called moment due to a couple. In other words, the magnitude of the third type of moment, the moment due to a couple, is simply the magnitude of the force multiply the short distance between these two parallel force lines. Okay? If you say, well, if this is a magnitude, how am I going to determine the direction for two-dimensional problem? That's also easy, because when you say this R cross F, that's a right-hand rule. So basically, the moment is always perpendicular to this couple plane and following the right-hand rule. So if you have these two special forces forming a couple, then the direction of the moment is perpendicular to this force plane, but following the right-hand rule, which means if this is the case, it's going to be going up. Okay, so the moment vector of the couple is independent from the choice of original you pick. So that means no matter what, the final result is independent this one, and that means it is a free vector that can be applied at any point you like, which basically gives you the same effect. So that's why the third kind of moment, we're no longer calling a moment of something about a point. We're no longer talking about something about a point. This time, we simply call moment of a couple. we are not going to identify any point because it's independent. Or we're now saying the moment about a certain point, right? So we just simply call moment due to a couple or moment of a couple. The reason we need to talk about, that's the other thing before I move to the next slide, talking about the reason we need to introduce this, is basically this one. If, say, we have one couple like this, okay? Or we have another couple like this. So each force in a different direction, but if this is a couple, this is also a couple, the effect is the same thing. In other words, as long as the moment due to the couple is the same, then F1 times D1 equal to FD times D2. F1 is the shorter distance for the first couple. F2 is the shorter distance for the second couple. As long as the results are the same, which means the moment is the same. Okay, so two couples lying in parallel planes, and the two couples have the same sense or tendency to cause the rotation in the same direction. Then we treat them equally. Now I want to tell the reason why we want to talk about the third type of moment, which is moment due to a couple. Why? You have enough reason to ask why. The reason is, you say, wow, what kind of chance I can see these two special cases in reality? We happen to see two forces parallel with the same magnitude but in the opposite direction. Is it realistic to see those real forces satisfying what we call the couple? It's very rare to see that, in fact, in nature. But it is very important, is because we want to achieve our final goal in this chapter, which I'm trying to move forces from one point to another one. And then in the middle process, I'm going to introduce the moment due to a couple. So it's a virtual one, because in reality, it's very hard to see two real forces in nature, in the object, and they are parallel in the opposite direction with the same magnitude. That's very rare. But that's a good technology, the skill for us to move force around. So let's see now why we need to talk about the third kind of moment, right? So this is a typical three-dimensional, for example, rigid body here. We have a force acting on point A. Let me see. Okay, we still have 4 minutes. We have a force acting on point A. So I want to move this force from point A to another point O. Okay, you don't ask me the reason. I'm going to talk about the reason in the next section. Okay, so let's say I just want to move this force from point A to another point. How I'm going to do it? It's pretty hard to do it unless you're going to introduce this third kind of moment. Okay, you want to move the force from A to O. Okay, first find out point O, and then you know what? I'm going to add two virtual forces at point O. I'm going to add two virtual forces at point O. Originally, there's no force at point O, right? There's only one force here at point A. But you want to move this force from A to O. Okay, I'm going to create, or I'm going to assume there are two virtual forces at point O in the opposite direction with the same magnitude, even with this. Then you say, whether you're going to add these two forces at this point or not, it doesn't matter, because it cancels out at that point. Okay? So this is equivalent to this one, although you see, well, there are three forces, but these two are canceling each other. So that's why this is equivalent to this. But now, once you agree this is equivalent to this, then I'm going to do something on this second part, on the second scenario. Because this time, I clearly see this and this form a couple. Originally, there's no couple in the first place. But if I add these two forces, now I can claim I can see a couple, because this is a negative F, this is a positive F. These two together form a couple. I'm going to erase these two forces. I'm going to write a moment here, which is equivalent to this one. So finally, you find what? This force is successful move from A to O, but you need to add a couple. The reason we want to talk about a moment due to a couple is simply because we want to manipulate forces from one point to another point. And that's the goal. You may say, why you want to do that? Well, if we're dealing with a lot of forces, acting on different locations, we want to simplify the problem, which is equivalent to an original one. Then we need to pick up a point. And then we're going to move all the forces from different point to that point. And that's why you have to learn this technique. And this technique involves the moment due to a couple. So last time I briefly explained this. This time I'm going to tell you more about this one. And then we have a lot of examples later on just for this part. Okay. At that time, of course, there's going to be multiple forces. Okay. So we have a rigid body, three-dimensional setting in general, and there is a force acting on point A, very general. And now I just want to move the force at point A to this force to move another point at point O. This point O is any arbitrary point. Okay? So how to do that? So first of all, at this point you want to move the force to, I want to add two imaginary or called virtual forces, okay, at this point. This is a real force, but actually there's no force, right? So I'm going to add two virtual forces. In other words, they are not real forces, right? I'm going to add two virtual forces, but in order to have this one equivalent to this one, then these two virtual forces must cancel each other. So then, of course, that's equivalent to the original one. So I'm going to have one force, another one. This is parallel to the original direction, and this and this have the same magnitude but in opposite direction. That's why this is canceling with another one. You may say, can I at this point add the two forces, two virtual forces in this direction? Of course, not a problem, but you cannot solve the problem. Okay, so if you say, okay, instead of having these two virtual forces in this original force direction, can I add another two forces at this point in this direction? The same magnitude, but in opposite direction. Is this equivalent? And the answer is yes, but it's no use. Okay, so we want to do something. Finally, we end up with something useful, right? So we want to add two forces, same magnitude, opposite direction, but both force line of this and this are parallel as well. Okay, so this one obviously is equivalent to this because you basically add these two forces, but they are canceling each other. Okay. Now, let's do something further based on this picture now. So now we have essentially three forces. But surprisingly, we find out this force and this force are forming a couple. Right? So based on the couple definition previously, if you have two forces parallel to each other, same magnitude, but in opposite direction, these two forces form a couple. If these two forces form a couple, then I'm going to use the couple to represent this two forces instead of plotting these two forces. So what I'm going to do is to erase this red color one and erase this red color force. I'm going to erase those two, but then I'm going to add the moment due to this couple. So that's why you have this force left. So this force is still here, because I'm not going to do anything about this force, but it's still here. But this and this, which form a couple, I'm going to use a moment due to this couple to represent. Okay? So finally you find out this originally I have one force acting on point A and equivalent to this scenario, but you look at this scenario more carefully, you have the same force with this one but acting at a different point, and that's exactly the point you want to move the force to. So you finally move this force from point A to point O, but you have to pay the price, and that price is this additional moment, which is the moment due to a couple. So how to calculate this moment? So this moment is basically R cross F. So what is R? R is exactly this R, because originally you have a force acting on the point A, that means point A is given, and you want to move this force from point A to point O. That means you pick point O. If you pick point O, then obviously you know how to calculate the distance vector from O to A. So this is called R. So R cross this F should be this moment. Okay? So you can say this moment is a moment due to a couple. You can also say this is the moment which is the moment of this force about this point. The same thing. Once we are successfully moving this force from one point to another one, then later on you will see how easy to deal with multiple forces acting on different locations, and then we can find out in the same rigid body there's only one equivalent force acting on one point you chose, and a corresponding moment. And that's the last part we're going to talk about in this chapter 3.